Learning Outcome 1-3. Determine memory, causality, stability, linearity, and time invariance, given an input-output definition of a system. In this video, we're going to focus on the linearity property, and we're going to focus on the mechanics of doing the proofs for linearity. Recall from a previous video that a system is linear if it satisfies two properties. We will focus on the mechanics of each property separately. First is additivity. If the response to x1 of t is y1 of t, and the response to x2 of t is y2 of t, then the response to x3 of t equals x1 of t plus x2 of t is y3 of t equals y1 of t plus y2 of t. So in this video, x is our input, y is our output. We can call our input x1, which will produce an output y1. If our input is x2, it'll produce an output y2. And if all goes well, if our input is x3, which is the sum of x1 and x2, it should produce an output y3, which is y1 plus y2. So again, let's look at this particular example of a system. Y of t equals 2x of t. In order to determine whether the system is linear, we'll check additivity. We will define y1 of t, y2 of t, and y3 of t. These are just repeating our definition of the system with our x of t and y of t with subscripts 1, 2, and 3. We're always going to do these three steps in our additivity proof. But exactly what we write over here will be dependent on what appears on the right-hand side of our system definition equation. The next step is to add the inputs. We're going to write out this step verbatim every time we do a proof. This will never change proof to proof. Once we've written it, we're going to use it by substituting it into the previous line and doing some algebra. The next step is to write out our output is a summation. Again, this is going to be verbatim, regardless of what we have for a system definition equation. We then will take our first two system definitions and substitute them into here. y1 of t was 2x1 of t, y2 of t was 2x2 of t, just from above, first two lines. We now are going to compare the response of our system to a sum of two inputs to the sum of those two outputs. And if they're the same, which they are in this case, additivity is satisfied. Let's do the same series of steps for a different system definition. Again, y1, y2, y3 are going to be always three things, but what's on the right-hand side is going to change from problem to problem depending on what we have for our equation, our input-output equation. The next step is verbatim. We're going to add our inputs x1 of t and x2 of t to form x3 of t. This is always the fourth line and is always written exactly like that. We then substitute it into the previous line, do some algebra, and then we move on. The next step again is verbatim. Add our two outputs. What are those two outputs? They're from the first two lines, so we will substitute them. y1 of t is x1 squared of t, y2 of t is x2 squared of t. And now we compare. Is the response to the sum of two inputs equal to the sum of the two outputs? We can compare these. Are x1 squared of t, x1 squared of t, those match. x2 squared of t, x2 squared of t, those match. But this portion in the middle does not match. Additivity is not satisfied, and therefore the system is not linear. Now let's check out the second property. We now want to see whether a system satisfies homogeneity or scalability. This says that if the response to x1 of t is y1 of t, then the response to x2 of t, which is a scaled x1 of t, will be y2 of t, which is a scaled y1 of t. Again, thinking about it in terms of our system inputs and outputs, Our input is x, our output is y. If we input an x1, we're going to get a y1 out. If we input an x2, which is ax1, we should get a y2, which is ay1. But we need to calculate what is ay1 of t, and is that going to be the y2, which is the response to this input. Let's look at the mechanics. We have an equation relating x of t and y of t. So we're going to take that equation and we're going to substitute it with subscripts 1 and 2. And this is always going to be the same two steps, but what's on the right-hand side will change depending on how our system is defined mathematically. The next step is verbatim. You will always write x2 of t equals a x1 of t. Then you will substitute that into the previous line. Now the next step is again to look at our output, being a scaled version of the output. Again, this is verbatim. Regardless of what your system definition is, it's always going to look like this. But we need our y1 of t from up above, which we'll substitute in. y1 of t is 2x1 of t. And we then compare the response of our system to our scaled input and see whether it is our scaled output. In this case, with a little bit of algebra, we can see that they do match. Scalability is satisfied. And because we also had additivity satisfied earlier, the system is linear. Another example, our system definition, x of t, y of t. We write out our system definition, but we use subscripts 1 and 2. These, again, are always the same two steps we're going to start with, but what's on the right-hand side is going to change depending on what we have as our input-output system definition equation. Our next step is verbatim. Look at the previous example to write x2 of t equals a x1 of t. And we then take this x2 of t and substitute it into the previous line and do some algebra. From here, we're going to look at our output and scale our output. Again, this line we write verbatim every time, but we need our y1 of t from the beginning, substitute it into here. y1 of t is x1 squared of t, and then compare whether the response to our scaled input is our scaled output. In this case, they are not equal, so scalability is not satisfied, and our system cannot be linear. Think through these steps. Some steps, the ones I've written in blue, are always going to be the same type of steps, but are going to depend on our system equation. The steps written in red are always going to be written verbatim. And we're always going to repeat the process of doing substitute, and do compare.